So we will have our first midterm exam tomorrow at 10 a.m. in the morning. So before I say anything about the exam, let me just go over our last Tuesday's lecture. So on Tuesday I talked about three-dimensional effects. So this is basically what differentiates a two-dimensional airfoil from an actual three-dimensional wing. Okay, so if you remember that lecture, basically if you have a three-dimensional wing, then at the wing tips, due to the separation between the high pressure and low pressure zone ending, such circular flows occur at the wingtip, and these circular flows causes the lift force to drop to zero right at the wingtip, and also causes the drag force to increase. And this is a big loss actually. So, but unfortunately we can't really do anything about that. For a real aircraft, for anything flying with the dynamic lift concept, such losses have to be there. And obviously these losses are not the same for all the wings. Especially if you remember our discussion on the aspect ratio. If you have a high aspect ratio wing such as this one, the area that is affected by these wingtip vortices will be a smaller part of the entire wing, as opposed to a low aspect ratio wing. So because of this reason, high aspect ratio wings are much more efficient in terms of aerodynamic performance. Okay, so starting from next week, I will show you an equation that quantifies the performance losses due to three-dimensional effects. So there will be a single equation, and this equation contains the effect of the losses, and this is the most important equation in aircraft performance. So throughout the entire semester, in everything we do, literally everything, in all our calculations, that equation will be the most important equation in terms of aerodynamic performance. Okay? So if you want to have a high performance aircraft, you should somehow make these losses smaller. And again, these losses determine the performance of your aircraft. Okay, so I will be talking about that after the exam. But today I would like to spend this 40 minutes we have on the exam, about the exam we're going to have tomorrow. So let me ask you if you have any questions. I posted you 4 exams, and one of them has solutions. Unfortunately, the others don't have solutions. So let me hear your questions. Okay, let's start with you. Okay, so you're talking about this question, right? Question 4. Okay, so let me read the question. In a wind tunnel test for a two-dimensional airfoil at alpha is equal to 0 degrees, the lift, drag, and pitching moment coefficients around the quarter-chord point are found to be, so these are the values found, where the positive sign for the pitching moment coefficient indicates a nose-down direction. Find the location of the center of pressure and tangent of phi, where phi is the angle between the resultant aerodynamic force and the chord line. Okay? So do you want me to solve this question? Yes. So did you try to solve this?
I still, because I understand what does visa and CO form. So what can I do?
Okay, so we have a 2D airfoil test in a wind tunnel. So let me just draw it here. So this is our airfoil, let's say. And it says that lift, drag, and pitching moment coefficient of forces, these forces and moments are measured with respect to the quarter chord point. So that means let this be the quarter-chord point. And we have a sensor here, and at this point we measure the forces and the moment. So what we measure is the aerodynamic forces, right? So there should be an aerodynamic force vector, and let this vector be that, R. And the reason I drew it behind the quarter-chord point is it says the pitching moment coefficient is 0.06. That means there's a pitching moment with respect to that point, and that the coefficient for that moment is this value, 0.06. And it says the positive sign indicates a nose-down direction. So for nose-down direction, to have a nose-down moment, the aerodynamic vector should be behind the quarter-chord point. So let me call this distance x, and let me write the components of this. So this is the drag force. This is the lift force.
Why it should be there? Because quarter-chord point is the center of all the pressures.
Well, not necessarily. We said for symmetric airfoils, the center of pressure is close to the quarter-chord point, and it doesn't change with angle of attack. But for cambered airfoils, it's not the case. Because in the question it says that there's a positive pitching moment coefficient, and it says positive means a nose-down moment. So for the nose-down moment, for the moment of the lift force to be nose-down, it should be behind the quarter-chord point. Okay, so anyway, so this is what we measure, right? So we measure the vertical force, Fv, the horizontal force, let me call that Fh, and then we measure let me call this just M. Okay, so since the airfoil doesn't move, net forces should be zero, right? So the aerodynamic force, the lift force, should be balanced by the reaction force at this point where we have our sensor, and the drag force should be balanced by the horizontal force measured at this point, and the moment of this lift force should be balanced by the moment applied at the point where we have the wing attached. So from here the
Why we have these forces Fh and Fb in the quarter-chord point? So what's the reason for these forces?
Okay, so let's say suppose that there is a wing, okay, and I'm holding this wing, okay. So güzel bir şey olsaydı. Evet. So okay, so let this be the wing in the tunnel, okay? I'm holding it from here. Okay? So if as I turn the tunnel on, some forces develop on the wing, right? Aerodynamic forces. And if I try to hold this steady, I should apply a larger force with my hand, right? Otherwise, these forces will try to move it. So if as the forces, aerodynamic forces develop on the wing, the same forces in the opposite direction should be applied at this point where it is held steady. Right? Okay, and the total force should be zero since it doesn't move. So this means that the force Fv should be equal to the lift force, and the horizontal force Fh should be equal to the drag force, and the moment should be equal to the lift times moment arm, which I call x. No. Okay, so let me just write it. So let me take this to be the positive direction, okay, for the moment. So this is in the positive direction, right? The moment due to the lift force. So I should write it as a positive term, L times X. And this moment is in the opposite direction, so I should write it as a negative moment, minus M. And the total should be 0. So from here, M should be equal to L times X. And M is in this direction, the opposite direction. So the lift force is trying to bring the nose of the airfoil down, and the force at the attachment point should be in the opposite direction. Okay? So let me just write my equations. So only the coefficients are given, right? So lift force should be 1 over 2 times rho times V squared times S times CL. By the way, you should all know this equation. I'm not going to give you this equation, and you will need to use this equation. So you should know this equation. Okay, and it's just a very simple equation. So, and similarly, drag should be 1 over 2 rho V squared S times CD. And the pitching moment should be equal to 1 over 2 rho V square S times so we use C bar for pitching moment and then Cm. Okay, so we are asked to find the location of center of pressure. So basically we are asked to find this x distance, right? Because if I know x, I will know the center of pressure. This point is Cp. So for that, let me use this equation here. M is equal to L times X. This should be equal to this times X. So let's see, I can just cancel all these terms here. V square, even the S term should disappear. So from here I can find X as C bar times Cm divided by Cl. And I know the values of Cm and Cl. Cm 0.06 and Cl is that much. Times C bar, and that's 0.24 C bar, right? Well, that C bar is the chord length. So this entire distance is C bar. Mean aerodynamic chord. And that C bar is in the moment equation. This equation contains C bar in it. So it turns out that X should be equal to 0.24 times C bar. So this distance is yeah, sure. Okay, so the moment equation contains the C bar term, and C bar is mean aerodynamic chord. So whatever the airfoil is, you put that C bar for that airfoil in that to find the aerodynamic coefficient. So we find that the center of pressure is 0.24% of the chord length behind the chord point. Almost. And there's another thing asked in the question. That was the angle, I think. and the chord line. So we are asked to find this angle here. Now for the second part, the tangent of that angle should be equal to lift over drag. And that will be equal to CL over CD, because everything else in these equations cancel out. And that's 0.25 divided by
Hocam, buradan sınavdım da, hocam şimdi yapamamış. Notlarda toplam boğuluklarla yakın bir bölüm var. Mesela arkadaşlar orayı tahmin. Toplam bir tamam. Pardon, toplam teknik tamam. Toplam ekval tamam. Ama toplam boğuluk tamamken nereye göre alıyoruz? Niye alıyoruz? Onun mantıklı bakmıyoruz. Sadece o bölümler. Yani bugün de bu şöyle o yüzden
okay, so if you are when you are taking the moment for an object that can move, you should always take the moment with respect to the center of gravity. In this case, it's not the moving object. It can freely rotate around a single point, which is the quartz chord point. And in such problems, you should take the moment with respect to that point where it can freely rotate. Otherwise, if this was an aircraft that can fly freely, then you should take the moment with respect to the center of gravity. Okay, is this clear? Okay, 2011, question number 5. Okay, so let's talk about this question. So if you look at the data given, we are given lift and drag measurements obtained in a wind tunnel at different speeds, right? So the tests were performed at 2 different speeds. The first one is at 10 meters per second. The second one at 50 meters per second. So normally, the aerodynamic coefficients should be independent of speed if the flow conditions are the same. But here, if you look at the data, you clearly see that they are not. The aerodynamic coefficients are different. That means the flow conditions are not the same. And this should give you a hint that we are given the dynamic viscosity value for the air, right? So we should calculate the Reynolds number. And these two tests, this graph and this graph are obtained for 2 different Reynolds numbers. Okay, so the first step should be to calculate the Reynolds numbers. So let me call the first one Reynolds 1. Okay, so I need your help here. Can you tell me the formula for this? So we have the speed, right, and then rho, and some distance, right, let me call c bar, over mu, right? I think this is the formula. So for the first one, it's 10, rho is 1.2. So the model tested in the wind tunnel has this much 0.25 chord length. Two times 10 to the power So can you quickly tell me what this makes? And there should be some zeros, right? Catch? 4. So this is the Reynolds number for the first test. In the second test, everything is the same except for the speed, right? Since speed is 50, it should be 5 times this. Okay, so we have test data for 2 different Reynolds numbers. These are obtained in the winter. Efendim? 75 olması gerekiyor değil mi? Pardon. That's the air density, and we take the unit for the air density is kilograms per cubic meter. So we have data for 2 different Reynolds numbers, and this is obtained in a wind tunnel. Now we have an actual aircraft flying. So to decide which one of these data is relevant to our actual flight, we need to calculate the Reynolds number for the actual aircraft. Okay, so let me call that RE actual. And let's see. So we have finite lift force, the full scale we can create while flying it. So this is the speed of the actual aircraft. It's 25. And air density is the same, I think. Yes, it's given to be the same. And the chord length is 0.5 for the actual aircraft divided by. And this makes 75 times 10 to the power 4, I think, right? Okay, so here we see that the Reynolds number for the actual flight is the same as the Reynolds number for the second test. So that means this data is relevant for our aircraft. Okay, so we can just ignore the first set of data because it's for a different Reynolds number. Okay, now since we have decided that, let's see what is asked. The maximum lift force. So for the maximum lift force, so the air density is given. We know what it is. It's 1.2. And the speed of the flight is given. It is 25 meters per second. And the wing surface area is given. So the only thing that can change the lift force is the lift coefficient. Okay, so and if we are looking for the maximum lift force, then we should be using the maximum lift coefficient in this equation. Since every other term in this equation has a constant value, we cannot maximize them. And if you put in the numbers here, 0.6 times 25 squared times, what was S? 2 meters squared times CL max. And since we decided that we should use this data, and the maximum lift coefficient is, we need to find the coefficient before we can use that. Let me just write CL max. But that's for the small scale version, wind tunnel model, not the actual aircraft. Doğru. So let me just put this equation here. I need to find the value of CL max, and the value of CL max will be calculated using this small wind tunnel model. For the small model, 900 is equal to 1/2 times 1.2 So I should find the value of CLmax from here. Bu hemen hesaplayan birisi olursa 12 1.2 olsa gerek. 12. So it should be 1.2. 12 is too big of a value to be a lift coefficient. Okay, now I put this CLmax value back into the above equation to find the maximum lift force for the actual UAV. I think it's the same, right? It's still 900. Bir yanlışlık yok değil mi? So the maximum lift force for the actual UAV happens to be the same value for the wind tunnel test, but it's just a coincidence. In this problem, it's just a coincidence that the numbers turn out to be the same. Şurada mı? Onu 1.2'ye bölüp yazdım ya direkt 0.6 diye. So this is the same as this thing here. So I have an additional 4 here, but 4 times 0.5 gives 2, and we should cancel this thing here. They will have the same lift coefficient, but not the actual lift value. So as I said, in this question, it's just a coincidence that they happen to have the same lift force, but normally only the lift coefficient should be equal. So this is our equation, right? So we always use this equation, and we use the values for the aircraft we have. If it's a wind tunnel test model, then we should use the surface area and speed, everything for that model. Efendim? So, because we are asked to find the lift force, so we should use the lift data. Right? Efendim? So there are 2 lift curves and 2 drag curves. Right? This is one drag curve, this is the second drag curve. And there are 2 lift curves. And these lift curves are obtained at 2 different Reynolds numbers. So that's why we calculated the Reynolds numbers for these 2 tests at first. Kaç? 2000? Okay, so let's quickly go over this question. So we are asked to compare the lift and drag forces of 2 different airfoils on each row. Okay, so in the first row, we are asked to compare the lift and drag force of these 2 airfoils. So the picture is not very clear, but what is different between these 2 airfoils is the second one has a greater camber. Okay, so they are both cambered airfoils. It's not very clear again, but you see the chord line, and it's obviously not a symmetric airfoil because the chord line is not in the middle. And if you compare, so let me just make it apparent here. So the chord line for the first one is here, and the chord line for the second one is here. And if you just look at the chord lines, you can clearly see that the second one has a greater camber. And since it has a greater camber, and the angle of attack is 0 for both of these two cases, and since the second one has larger camber, it should produce more lift force, right? So there should be a smaller sign here. And similarly, the drag force should be greater for the second airfoil as well, just because it has a larger lift force. That's not obvious. Actually, it's a very good question. And when I asked this question in the exam, I didn't take this part into consideration. So whether the student puts greater or larger or equal to, I gave the full credit for that. Again, it's not really obvious to see you, but yes, I mean, I think best to put a question mark there. Okay, in the second one, the airfoils are the same. They are both symmetric, and they have an elevator at the back. It doesn't matter. You just have an airfoil and a trailing edge device. And they are both symmetric. And again, from the picture, you see that this is deflected more. Okay, so that means the flow will be deflected by a large amount on the second airfoil, which means that there will be a larger force on the second one. Again, this should be less. And similarly, the drag force is smaller for the first one because it's... but again, you can put a question mark here as well. It's not... Evet. Doğru. Doğru ama dediğim gibi yani burada da soru işareti var ya da onu puanlamaya dahil etmedim başka bir deyişle. Okay, in the third row, the airfoils are both symmetric and angle of attack is both 0 for both of them. And clearly the second one is thicker. But since they are both symmetric and the angle of attack is 0, they both create no lift force, right? So for this one, it should be, they are equal to each other, and in fact, they are both equal to 0. And however, since the first one is thinner, the drag force should be smaller for the first one. So it should be like this. Bu üçüncü soruda mı? Yani bu üçüncü sırada. Evet. Well, but you can obviously see that this is the leading edge, this is the trailing edge. If you just draw a straight line between the two. Okay, so in the fourth case, we have the same airfoil, and the first one is at a positive angle of attack, while the second one is at 0 angle of attack. And obviously the first airfoil should create more lift force. And in fact, the lift force for the second one should be 0. And in terms of drag forces, the drag force for the first one should be greater than the second one because it's... but again, if you can put a question mark there as well, because I really didn't stress the drag force too much in this course. We always talked about the lift force. Okay, so when we come to the last case, we have the same airfoil at the same angle of attack, which is 0. But the second one is sees a larger free stream velocity. And since we have a symmetric airfoil at 0 degree angle of attack, we should put the lift force should both be equal to 0. And the drag force for the second one should be larger, just because it has a larger dynamic pressure. Bir daha söyle. Gerekiyor, doğru. Yani onu da öyle yapalım o zaman. So this is what should normally be. Bayağı güzel soruymuş değil mi ya? Beğendim size. So if in the third row, if there was an angle of attack, then we wouldn't be able to say anything for sure. So in that case, it would be just best to put a question mark, because the angle of attack will obviously give you more lift force, but you have two airfoils with different thicknesses. So we can't really say anything for sure. But what I put here, all these things can be said for sure, except for these question marks. So these question mark cases are not that obvious. But everything else here, you can say that for sure without any hesitation. You can say that. Buradaki resim biraz daha net sanki, değil mi? Actually, we can just very quickly complete this. So we have positive chamber, 0 degree angle of attack. Due to positive chamber, lift should be greater than 0, and drag should be greater than 0 as well. And in this case, we have negative chamber. So the angle of attack is 0, but lift should be negative for that, and drag should always be positive. In the second row, a symmetric airfoil, but a positive angle of attack, a positive lift, drag positive as well. And this one, negative angle of attack, so lift should be negative due to that, and drag again should always be positive. The third line, so flow is deflected upwards, that means the force should be downwards, a negative lift force, a positive drag force. This is the opposite. Lift should be 0, drag should be positive. And in this last case, there is no flow. And in this case, there should be no net aerodynamic force, right? They should both be 0. Okay, so let's take a look at this sixth question. Oh, well, the sixth question is related to the first midterm, because there's it talks about these Oswald efficiency factors and the aspect ratio. So we haven't seen that equation yet. So this equation is not in the scope of this midterm. Evet. Yani lift küçültü demek aşağı doğru demek. Hı hı. Okay, do you have any more questions? We will see that. So as I said at the beginning of this lecture, so the most important thing that determines aerodynamic performance is the 3D effects, and the equation that comes out of that is the equation that relates lift to drag. So once we see that equation, you will clearly see that there is a relation between the lift force and the drag force, and that relation is important. Obviously, we always want more lift force, but less drag force. Hı-hı. Yok. Yani onlar yok, hem de koyamayacağım maalesef. Ha, bunları koyarım. Trim tab. So we have 3 minutes, and it's really, I can't really explain it in 3 minutes, but I can explain it longer if you want. In the break, I can explain that. Okay, so we have another hour, and if you want, you can stay and we can keep talking. Otherwise, I will be waiting for questions from the students in the second hour as well. Ya çok yok da daha yarın sınavın sorularını hazırlamadım. Onları falan hazırlamam lazım. O yüzden söz veremiyorum yani. Var. Onları koyacağım ama daha sonra. Şimdi özellikle kafa karışıklığı olmasın diye koymadım. Çünkü direkt bu sınavla alakalı yoktu. İkinci midterm için koyacağım onları. 2'de 3'te sanat